So now your second podcast, topic 1, lesson 1. We're on part B of this, and now we're going to talk about mixtures. So just as a reminder, before we were talking about substances can be pure substances, and those pure substances can either be elements or compounds. Now we're going to talk about when a substance is not a pure substance, and that is when it is a mixture. So a mixture, the definition, I have 4 bullets here for you to look at, and again, you remember you can always pause and go back and rewind if you need to write these things down, because you should be writing these down as notes. Tomorrow we will be going over them, perhaps a pop quiz on them, just to make sure that you were taking notes. So again, please make sure that you are taking notes as you're watching these podcasts and writing down any questions that you have, things that don't seem to make sense to you or you need more clarification on. But anyways, a mixture. A mixture is 2 or more substances that are physically combined. And I'm going to see if I can write that physically in here. Need to get myself a better pen. But 2 or more substances that are physically combined. And we will talk about what I mean by physically versus chemical properties and physical changes and chemical changes later on in the podcast. The composition can vary, which means it can be different throughout. Let me give you an example, first of all, of the 2 or more substances being combined physically. Air is actually an example of a mixture. Most people don't think it is because they can't see it, or it doesn't look chunky, or it looks the same throughout, but it is an example of a mixture because you've got hydrogen in there. You've got, let's say you have some water vapor in there because it's really humid, like today. Let's just say you also have, which you will, have some nitrogen in there. So you have a whole bunch of different pure substances that are combined physically, but I could actually take them out. For example, if it gets too humid, that water vapor that's there, if it gets too humid, those water vapor gets condensed together and it's actually going to rain, and that's going to come out of the air. So again, clouds are an example of a mixture with air, and you can see the dust particles. So 2 or more substances physically combined. The composition can vary. For example, I can have smoky air versus clearer air. If you're at the campfire, it's still going to be air, but if I took a sample where I was sitting versus where somebody else was sitting, probably odds are where I'm sitting is where the smoke is being blown to for some reason. So it's going to be a little bit more smoky. Mixtures can be separated by their physical properties. So you can actually go ahead and take the fact that these substances retain their physical properties and they're different, and you're able to separate them according to that. Let's just say, for example, let me give you something different besides air. Let's just talk about dirt, for example, because dirt is another example of a mixture. I can separate dirt out because by different particles, by what they look like. I've got some clay here, I've got sand, I've got like really nice black dirt. I can separate it that way, or I can separate it by the fact that I want really, really fine dirt, so I'm going to get all the stones out of the dirt. So it can be separated by physical means. And lastly, each substance is going to retain their properties even after they are combined. So let's just say I take some rocks and clay and sand and I put them together and I make a mixture of them. Well, the sand didn't all of a sudden get more clayey, and the clay didn't all of a sudden become something different. They retain their properties, and because even though they are mixed, I can still separate them out. And let's go back again to this air thing. The hydrogen keeps its properties, the water keeps its property, nitrogen keeps its properties. All those things, all that stuff, all that matter that is in the mixture, all those pure substances, whether they be elements or they be compounds that are in that mixture, have their own characteristics and their own properties, and they can be described in their own ways, and because of that they can be separated out. I can distinguish them and actually get them out by themselves. So on the last slide I talked about a whole bunch of different types of mixtures. So I'm going to ask you, what is different about these mixtures? If I can say that air is a mixture, and that pizza is a mixture, and that dirt is a mixture, and that Kool-Aid that you drink in the liquid form is a mixture. What is different about these mixtures? Two of them would be classified in one aspect of a mixture, and the other two would be a different type of mixture. So again, just like when we talked about pure substances, and that there are two types of them in the previous podcasts, a pure substance could be an element or a compound. Here we're talking about mixtures, and they can be categorized in two different areas. Mixtures can be homogeneous or heterogeneous. Now I want you to remember from your past subjects how to break apart words and use what you've previously learned to figure out what the new words mean, such as homogeneous or heterogeneous. Well, you have learned about homogeneous and heterogeneous when you were in biology class and you talked about genetics. You have heterozygous and homozygous is what they talked about. Remember the big T or big T little t? So what I want you to think about is that back in biology, the big T or the little t would be homozygous, and big T little t would be heterozygous. So back in bio, this would be homozygous, or this would be homozygous, and this would be heterozygous. So now you can know what the terms homo and hetero mean. Homo means the same, and hetero means different. So with that knowledge, you can take and say, okay, I'm going to apply that to these terms, homogeneous and heterogeneous. So homogeneous mixture is classified as the compound or the components being uniformly mixed. Uniform. Now we know what a uniform is here at Springs, right? But uniformly mixed means that it's going to look the same throughout. Heterogeneous is the exact opposite, so I'm not even going to attempt to draw it in here, but heterogeneous means that it is not uniformly mixed. They are going to be different throughout. In a homogeneous mixture, every sample that you take from that mixture is going to be the same. It doesn't matter what you do. If I take it from the top or the middle or the bottom, wherever I take a sample from, all those samples are going to look the same because they were uniformly mixed. You can't say that about heterogeneous. The samples can be the same, they can be different, depends upon where you take the sample from. So therefore it's not uniformly mixed because it depends on where you take it from. So now let's go back to those 4 examples that I asked you about. Air. Where would air be classified? Where would dirt be classified? Let's see, where would Kool-Aid be classified? And then where would pizza be classified? So, air would be here, and Kool-Aid would be here. And over on the heterogeneous would be dirt and the pizza. One misconception that I want to make sure is understood, everybody seems to think that for some reason if you are liquid you are homogeneous, and if you're a solid you're heterogeneous. And so for the examples that I gave you, that's not that kind of goes with what the misconception is. Kool-Aid, for example, is actually not a liquid. It's what we call aqueous, and that's an AQ, which means it's dissolved in water, which means you have water and then you have bunches or little bits of Kool-Aid that is dispersed throughout that water and dispersed so small that you can't see it, but it is evenly. So Kool-Aid would be an aqueous solution because it's a mixture of water and of that Kool-Aid mixture. And now if I left that out or if I boiled that, I could get all the water back out of it, and I'm going to have that Kool-Aid powder left at the bottom of my cup. Air is a gas, but solids can also be homogeneous as well. And I want to make sure you understand that. And heterogeneous doesn't have to just be solids. They can be also homogeneous as well. For example, I can take this air, and if I said smoky air, that would maybe then be a heterogeneous mixture, because if I take the air in different spots, it's going to have different particles in it. So you got to be careful in terms of classifying whether it's homogeneous or heterogeneous. To make a diagram of something that's heterogeneous, well, let's do homogeneous first. So, whoops, I didn't mean to do that. Let's see if I can get this going here. So if I do a homogeneous and I want to draw it, I would make sure that whatever I draw, it was evenly distributed, and I don't know if you can see, trying to make the dots be evenly distributed throughout. Now hetero would mean that I would have dots, and maybe they're all in one area, and they get a little bit less as they go somewhere else. But they're all kind of more done in one, whereas over here, as I tried, it was the same composition throughout. Okay, so for this next slide, what I want to do is I want you to realize that mixtures can be separated physically using differences in their physical properties between the substances that make it up. So if you have like 3 different substances to make up this mixture, those 3 different substances are all different. They have 3 different properties. It's like 3 different people, and they have 3 different personalities, and you could probably separate them up according to their personalities. And this is what I mean by this. The mixtures can be separated by the individual physical properties, because when they come together, they don't change. They don't change their physical properties. They are strong in that they keep their identity. So I want to go through some properties and the processes that are used to separate the mixtures using that property. So let's see, for the first one, let's type these in as we go. So for the first one, the first property I want to do is size. So the process that you would use to separate something according to size is called filtration. So please understand that property is a noun, whereas filtration is what you do. It's going to be the verb. So I want to make sure you understand the difference between the property and the process that is used. Another property that is used, would be magnetism. And there's really not a property that would be going with that. So when I go over to the side over here, I'm just going to, oh goodness, I'm just going to put a slash for its process. Another property would be color. And again, really don't have a specific process for separating according to color. You just look at it and you do. Another one would be miscibility, which that might be a new vocabulary word for you, miscibility. And what miscibility means is that you're able to mix it. So under miscibility, you might want to write down that miscibility means the ability to mix. So the process that you use to separate whether if one was miscible and one was immiscible, in other words, or the two substances were immiscible together, such as oil, oil and water. They don't mix together well. They are immiscible. So how would you separate them? You do decanting. Excuse me. The next property is density. And again, not going to go through a process of how you then would separate according to density. It'd be nice if I could spell it right though. You'll find that out, that I have sometimes some issues with spelling. Another one, I want to go through two more, would be solubility. And if you don't know what solubility means the ability to dissolve or to dissociate in order to break a compound up, a substance up. So the process that, one of the processes that you can use to separate according to solubility, which you can do and might be doing tomorrow in class, would be chromatography. And if you are interested in like CSI or anything like that, chromatography or gas chromatography would be something that you might look into. But we will be doing chromatography in class tomorrow. Going back to one other property, and there's many, many different properties. This is just a list of a few of them. One other property that is worthy of noting is boiling point. Because no matter how many times I say it, everybody wants to think that boiling something is a chemical change, which it is not. And you know that because when you boil, say you boil water, can you get that water back? Yep, I can collect that steam and condense it and go right back to water. One of the ways to tell whether it's a physical property or chemical property, not always, but often, is that you can reverse it. So boiling point, in freezing point, melting point, all of those where they change phase or change from a solid liquid to a gas, you can always get them back. And so that's actually a physical process and or physical property. One of the processes that is used to separate according to boiling point is called distillation. And that's the way that we get actually the gas that we need and the asphalt and all those different things. They do fractional distillation. They take all the junk, all the crude oil out of the ground, and then they put it in this big distillation factory, for an easier way of saying it, and they boil off the first, like the kerosene and then the gasoline, all the really light things that is in that crude oil, the low boiling points, and they recondense them and collect them, and then they boil off the next thing, and at the end they're left with just the mixture was just a gunk of really, really heavy stuff that it's very, very hard to boil, and that's the stuff that they make that asphalt out of. But we first get like our kerosene, our gasoline, and our butane, and all those different very light gases. We first get those off of the crude oil first through distillation. So my question is, could you draw a particle diagram of a mixture of two substances composed from these two atoms? And this is actually a question that was on my semester exam, or actually it was a cumulative exam at the end of the year. And for some reason, it kind of stumped a few people. So what I would like to do is see if you can do it. So take a second, pause, and see if you think that you would be able to do this and how you would do this. Okay, so this is what I would do. Now, first of all, a mixture means you have to have two or more pure substances. So I'm first going to say, okay, I'm going to take my one atom, and then I'm going to make, that's my element, and I'm going to make a compound. Now remember, that's just an element because they're two of the same atoms put together. They have to be different. So I'm going to make a compound. My Mickey Mouse here. So now that I've made my element and my compound, to make a mixture of it, it simply is, I'm just going to make my box, make my box here, and I'm going to put a few of my elements with a few, maybe a couple, just for time purposes, of my compound. And there we have a mixture, which, by the way, I kind of made, I would say that that's not evenly distributed, so what kind of mixture would it be? It would be heterogeneous. I could have made two different compounds and put them together, maybe something like this, and that's also a mixture. Remember, a mixture is two or more different pure substances put together. And there you go. So for these last three slides, I'm just going to give you some definitions, some notes for you to write down, just describing the difference between physical changes and physical properties. So the definition of a physical change is one in which there is not a change in formula. You only are changing from one form to another, like going from a solid to a liquid or a liquid to a gas. You're not changing the formula. For example, if I have solid water, which we normally say as ice, and I change it to liquid water, which is what we normally just say as water, it still is water. It still is H2O. So it just changed its form, but it did not change its formula, and therefore it is a physical change. A chemical change is indicated by, let's say, chemical A changing completely into chemical B. It no longer has the same properties, it's completely different, and has a completely different formula. So that is what a chemical change is. And in the next slide, I'm going to talk about how you can see evidence that a chemical change has occurred. First off, you're going to see possibly that a gas is given off. Now, one of these pieces of evidence is not enough to say that a chemical change occur. The more of these that you have in conjunction with the others, you are more apt to be able to say, yep, that's definitely a chemical change is occurring. But any one of these could be evidence of a chemical change. Second, heat or light changes. Having light given off, heat given off, or actually heat absorbed, exo or endothermic, giving off heat or absorbing heat. Any kind of color change, but this is the one I want you to make sure that you are careful with, because color change happens to many things, but it doesn't necessarily mean that a chemical change is given off. And for instance, Kool-Aid, making Kool-Aid, the water went from clear to now it's pink. That's not a chemical change, because we know that we just made a mixture and it just dissolved, and I can get that stuff back again. So that's not a chemical change. Precipitate being formed is another. And precipitate is probably a new term for you. And what precipitate means, it means that a solid has been formed from two aqueous solutions, or solutions where something was dissolved in them. So they look like, for right now, for your purposes, two liquids coming together, and all of a sudden you have this solid. It's usually in a powder form, and it makes the solution look very, very cloudy. And if you let it sit, all that cloudy stuff would go to the bottom, and so all the powder would be on the bottom, and the top would be whatever the liquid color normally would have been. Sometimes things like, everybody thinks of gas given off as bubbles. That's an example, and it is, of gas given off. But also, you gotta think about maybe smell. Like when something is rotting, which is a chemical change, it smells. Why? Because a gas is being given off, and that's what you are smelling. So evidence can come in many different forms in terms of the gas, but these are the pieces of evidence, or sorry, 4 pieces of evidence that you want to be looking for to see if a chemical change has occurred. And I will be putting some video in there for you to be seeing each of these, or at least, yeah, each of these evidences of chemical change.
This is an example of a chemical change. You see, I went to my favorites, chemical supply store, that would be the grocery store. And I bought some baking soda and some vinegar. Probably a lot of you have seen this. If I take some vinegar and I pour some vinegar into the Erlenmeyer flask, this is a Erlenmeyer flask, and then I add the baking soda to it, we'll see a chemical change. And I will know it's a chemical change, and I'll tell you why in just a second. Because, as you can see, it's fizzing right here. It's producing a gas. It's bubbling over, as you can see, and a gas is given off. So one indicator of a chemical change is that a gas is given off.
All right, we're going to perform one more chemical reaction, and we're going to see another chemical change, and let's just do the reaction, and we'll talk about it when it's done. I got my trusty little torch here, and we're just going to light a piece of magnesium, and it's going to react with the oxygen in the air.
That is amazing.
Ooh, so
that
bright.
is so bright, Mr.
So we
Sam.
can see there's light being given off, and I can feel the heat being given off from here as well. So light and heat being given off, those are two indications that a chemical reaction is taking place. You can also see we had a piece of shiny metal to start with, and now we've got a white powder that's left over. So we also have a color change. This is magnesium oxide. That's what happens when you combine the magnesium with the oxygen in the air. You form a new chemical substance.
Cool. We've got amazing help.
We're going to do another chemical change. This one we're going to mix lead nitrate and potassium iodide. And it's going to form a yellow precipitate, which will also change the color.
Very cool.
It looks like
So why is that an indicator of a chemical change?
it is an indicator of a chemical change because it changes color and it also forms a precipitate.
Now, what's a precipitate?
Precipitate is any kind of solid, or it looks like the cloudiness of this one also.
So if that's set for a long period of time, what would you see?
You would see a solid or like a powdery substance settled at the bottom of the liquid.
And it would be clear at the top. So it'd be yellow, it's like a yellow powder. They actually use this substance, or they used to make paint.